Good day, everyone. Good day, sir. My name is Nicole Joy Imbinuluspo, and my topic is about elastic collisions and inelastic collisions in one dimension, 8.4 and 8.5. So I'm going to start at 8.4 elastic collisions in one dimension. So our objectives for today is to describe an elastic collision of two objects in one dimension, define internal kinetic energy, derive an expression for conservation of internal kinetic energy in a one-dimensional collision, and lastly is to determine the final velocities in an elastic collision given masses and initial velocities. So, next is what is an elastic collision? Elastic collision is one that conserves internal kinetic energy. Internal kinetic energy is the sum of the kinetic energies of the objects in the system. So we need to remember that. Now in figure 8.6, an elastic one-dimensional two-object collision is shown here. And the momentum and internal kinetic energy are conserved, which means that in elastic collision, momentum and internal kinetic energy is always conserved. That is what we need to remember in elastic collision. So in here in the figure 8.6, mass 1 pushes forward and mass 2 is facing forward. So there is no collision yet. So that would be P1 plus P2 equals P total. And we need to remember also that in elastic collision, there is no net force, since in the collision here, it is a frictionless surface, so there is no external force or friction exerted. Next, after the collision, the formula would be kinetic energy prime 1 plus kinetic energy prime 2 equals kinetic energy 1 plus kinetic energy 2, since after the collision, there is an internal kinetic energy conserved. So our momentum would be P prime 1 plus P prime 2 equals P total. So as we observed here, the mass 1, the first object, bounces backward, while the mass 2 pushes forward. So in a collision, we would understand where the object would go. Is it either bounce backward or either pushes forward, or it would just stick together? It depends on the collision. So in here, it bounces backward, the first object, and the second object pushes forward. So our equation for conservation of momentum for two objects in a one-dimensional collision is P1 plus P2 equals P prime 1 plus P prime 2, which is there is zero net force, since it is no external friction or force that has been exerted. So if we are going to expound it, momentum is m1 v1 plus m2 v2 equals m1 v prime 1 plus m2 v prime 2. So again, there is no net force. The primes indicate the values after the collision. By definition, an elastic collision conserves internal kinetic energy, and so the sum of kinetic energies before the collision equals the sum after the collision. So we need to remember that internal kinetic energy is the sum before and after, which should be equal. So since kinetic energy's formula is 1 half mv squared, so it's gonna be 1 half m1 v1 squared plus 1 half m2 v2 squared equals 1 half m1 v prime 1 plus 1 half m2 v prime 2 squared. That is in two-object elastic collision. This expresses the equation for conservation of internal kinetic energy in a one-dimensional collision. So that's it. So here in example 8.4, we're going to calculate velocities following an elastic collision. So calculate the velocities of two objects following an elastic collision given that our mass 1 equals 0.500 kilogram, our mass 2 is 3.50 kilogram, our velocity 1 is 4 meter per second, our v2, our velocity 2 is 0 since the second object is initially at rest. So we are going to solve that. So now we're going to solve the example 8.4 of the elastic collision. So in the textbook, as you have seen there is no proper computation on where the book get the -3 on in the velocity prime 1. So we're just gonna solve it in a simplified version to understand it thoroughly. So our given again is our mass 1, 0.500 kilogram. Our velocity 1 is 4 meter per second. Our mass 2 is 3.50 kilogram, and our velocity 2 is 0 since the second object is initially at rest. So what we're going to find here is the final velocities of the two objects after the collision. So in order to find that, we're going to use this formula. Our mass 1 v1 plus m2 v2 equals m1 v prime 1 plus m2 v prime 2. So we're going to substitute the given to the formula. Our mass 1 is 0.500, velocity 1 is 4, mass 2 is 3.50, velocity 2 is 0, our mass 1 0.500, and we're going just copy this v prime 1 and v prime 2 since we do not know what is the value yet. So we're just gonna solve that. 0.500 times 4 is 2, 3.50 times 0 is 0, and we're just going to copy this because we do not know the value of the final velocities yet. So what happened here? We're just gonna have 0.500 v prime 1 plus 3.50 v prime 2 equals 2. So next, we're going to solve for the velocity. So we're going to use this formula, v1 plus v prime 1 equals v2 plus v prime 2. And we're going to substitute the given to the formula here. So we're going to have 4 meter per second for the velocity 1, and we're just going to copy the v prime 1 here, and v2 is 0, and we're just going to copy the v prime 2 here. Now, since we are finding the velocity, we're just going to transfer the v prime 1 to the left of the equals. So it's gonna be negative v prime 1 plus v prime 2 equals 4 meter per second. So after that, we were going to multiply this to 0.500, which is our mass 1. So that would be 0.500 v prime 1 plus 0.500 v prime 2 equals 0.500 times 4 is 2, so equals 2. Now we're just going to copy here and here. We're just going to copy that for get the sum. So 0.500 v prime 1 plus 0.500 v prime 1, we're just going to cancel that out because it is 0. And 3.50 plus 0.500, that would be 4 v prime 2, and 2 plus 2 equals 4. So what we're gonna happen is we're gonna divide it with 4. Then you can see that here. V prime 2 would be 4 divided 4 is 1. So 1 meter per second is our velocity prime 2. Now, since we have the b prime 2, we're just going to substitute that. Here, what just we found here, negative v prime 1 plus v prime 2 equals 4. So we're just gonna move the 4 to the right in order to find the v prime 1. So that would be negative 4 since we moved that, plus 1, which is, we recently found that it is v prime 2 equals v prime 1, which is the one we are searching. So that would be negative 4 plus 1 equals negative 3 meter per seconds. That would be our v prime 1. So now we already have the values of the v prime 1, which is negative 3 meter per seconds, and our v prime 2, which is 1 meter per seconds. Now all we're going to do is to check if our computation is right, since we use the simplified version of that formula. Now we will going to substitute our calculation, or the given and our calculation, to the formula. So our mass 1 is 0.500 kilogram, our V1 is 4 meter per second, plus our M2 is 3.50 kilogram, our velocity 2 is 0, equals M1, again 0.500 kilogram, our velocity prime 1 is negative 3 meter per second, plus our M2 3.50 kilogram, and our velocity prime 2 is 1 meter per second that we just recently found. So that would be 0.500 times 4 is 2, 3.50 times 0 is 0, so that would be 2 plus 0 is 2. And then 0.500 times negative 3 is negative 1.5. Then 3.50 times 1 is 3.50. So that would negative 1.5 plus 350 equals to 2. So it has been said that the before collision should be equal to the after collision. Then we know that our calculation is correct. Okay, now that we have the final velocities of the two objects, which is the first object negative 3 meter per seconds, and the second object is 1 meter per second. So what does this mean? This means that the negative 3, which is the first object, bounces backward because based on its size, it's only 0.500 kilogram compared to the larger object, which is 3.50 kilogram. So the 3.50 kilogram pushes forward, but only a little. It is only 1 meter per second because the second object is larger than the first object. So that would be all for the elastic collision. Okay, now we are in 8.5 in elastic collisions in one dimension. So our objectives for today is to define an elastic collision, explain perfectly in elastic collision, apply an understanding of collisions to sports, and lastly is to determine recoil velocity and loss in kinetic energy given mass and initial velocity. So what is an elastic collision? An elastic collision is one in which the internal kinetic energy changes. It is not conserved. So the main difference between elastic and inelastic collision is that the inelastic collision, the internal kinetic energy changes. It is not conserved. So, perfectly inelastic collision is a collision in which the objects stick together is perfectly inelastic. So, we say it is perfectly inelastic when the two objects stick together perfectly. So, that is perfectly inelastic collision. Now, in figure 8.8, an elastic one-dimensional two-object collision, we would see that before our first object heading forward and our second object is heading backwards for a collision. So that would be P1 plus P2 equals 0. And our internal kinetic energies formula is mv squared, and again there is no net force. It is 0 because it is a frictionless surface. Now after, or when the collision occurs, the mass 1 and the mass 2, or the first object and the second object, sticks together. So when it sticks together, there is no velocity since they are stuck. So that would be v equals 0, and our internal kinetic energy prime is 0, and that would be p prime 1 plus p prime 2 equals 0. So in here in our figure, momentum is conserved, but internal kinetic energy is not conserved, means it changes. Two objects of equal mass initially head directly one another at the same speed. The objects stick together, which is a perfectly inelastic collision. And so their final velocity is 0, and the internal kinetic energy of the system changes in any inelastic collision and is reduced to 0 in this example. So now, let's have an example in 8.5. We are going to calculate the velocity and change in kinetic energy in elastic collision of a puck and a goalie. RA, find the recoil velocity of a 70-kilogram ice hockey goalie originally at rest, who catches a 0.150-kilogram hockey puck slapped at him at a velocity of 35 meters per second. Under B, how much kinetic energy lost during the collision. Assume friction between the ice and the puck goalie system is negligible. So, now our before, again, though there is no net force, so that would be 0, and our momentum is P1 equals P total. So in before, our mass 1 seems to be approaching the ice hockey goalie, and our ice hockey goalie is at rest, so that would be V2 equals 0. Now after, we have here the ice hockey goalie catches the hockey puck, so that would be v prime 1 equals v prime 2 equals v prime. It is because the v prime 1 and the v prime 2 is just the same, so we will just gonna call it v prime. Now in kinetic energies, kinetic energy prime, internal kinetic energy prime is less than the internal kinetic energy, since we know that in inelastic collision there is a change, and since it is less than, we could understand that the internal kinetic energy on the after is lost since it is less than, so it is decreased. So then our momentum is p prime 1 plus p prime 2 equals p total. Now let's proceed to our solution for A, which we are asked to find the final velocity. So momentum is conserved because the net external force in the puck goalie system is 0. Conservation of momentum would be P1 plus P2 equals P prime 1 plus P prime 2. Now if we are going to expound the momentum, it would be m1 v1 plus m2 v2 equals m1 v prime 1 plus m2 v prime 2. Because the goalie is initially at rest, we know because the goalie catches the puck, the final velocities are equal, or v prime 1 equals v prime 2 equals v prime. So there would be no distinction if it is 1 or 2. We're just gonna have v prime. Thus, the conservation of momentum equation simplifies to m1 v1 equals m1 plus m2 times v prime. Solving for v prime yields v prime equals m1 over m1 plus m2 times v1. Now, we are going to substitute the given to the formula. So entering known values, we get v prime equals 0.150 kilogram over 0.150 kilogram plus 70 kilogram times our v1, 35 meter per seconds. So our answer will be 7.48 times 10 to the power of negative 2 meter per second. So now that we have found the final velocity, we will going to solve for the b, which we are asked to find the loss of internal kinetic energy. So before the collision, the internal kinetic energy of the system is that of the hockey puck because the goalie is initially at rest. Therefore, internal kinetic energy initial would be 1/2 mv squared equals 1/2 times 0.150 kilogram times 35 meter per second squared. So if we're going to calculate that, we are going to have 91.9 joules since our kinetic energies as a unit is joule. So after the collision, the internal kinetic energy is internal kinetic energy prime equals 1/2 m plus m capital V times v squared. So it is m for the mass 1 and capital M for the mass 2. So if we are going to add the two masses, we would get 70.15 kilograms. So that would be 1/2 times 70.15 kilogram times 7.48 times 10 to the power of negative 2 meter per second, since it is our value of our final velocity that we have just recently find here. Now, since we are asked on the loss of internal kinetic energy, we are going to subtract. The change in internal kinetic energy is thus internal kinetic energy prime minus the internal kinetic energy initial. So that would be 0.196 joule here for the internal kinetic energy prime minus the 91.9 joule, which is our initial kinetic energy, internal kinetic energy. So after subtracting, we get negative 91.7 joule. Now, what does this mean? This means that the negative 91.7 joule is the energy that is lost during the perfectly inelastic collision. Okay, now let's have another example. We are going to calculate the final velocity and energy release in two carts collide. Okay, our situation would be the two carts collide inelastically. The cart 1, denoted as mass 1, carries a spring which is initially compressed. During the collision, the spring releases its potential energy and converts it to internal kinetic energy. The mass of cart 1 and the spring is 0.350 kilogram. and the cart and the spring together have an initial velocity of 2 meters per second. Cart 2, denoted in mass 2, has a mass of 0.500 kilogram and an initial velocity of negative 0.500 meter per second. After the collision, cart 1 is observed to recoil with a velocity of negative 4 meter per second. So, what are we going to find? We are going to find the final velocity of cart 2 and the energy released by the spring, assuming all of it was converted into internal kinetic energy. Now, let's have our solution for A, which we are asked to find the velocity of the second object in the final. So, solution for A, as before, the equation for conservation of momentum in a two-object system is m1v1 plus m2v2 equals m1v'1 plus m2v'2. The only unknown in this equation is v'2. Solving for v'2 and substituting known values into the previous equation yields, so this is our equation, v'2 equals m1v1 plus m2v2 minus m1v'1 divided by m2. We are going to substitute that to our given. Our mass 1 is 0.50 kilogram. Our velocity 1 is 2 meters per second plus 0.500 kilogram, our mass 2, or cart 2, times our velocity 2, which is negative 0.500. This is negative because the cart 2 is going backwards. And then minus or divided by 0.500 kilogram, which is our mass 2. Now, we got to minus 0.50 kilogram, which is our mass 1, times velocity prime 1. Our velocity prime 1 is negative 4 meter per second, which means that it bounced back. It's again on the back since it is negative. Divided by m2, which is 0.500 kilogram. So, calculating that, we would get 3.70 meter per second. So, our final velocity for the cart 2 or the second object is 3.70 meter per second. So, now we will going to calculate for the B. The internal kinetic energy before the collision is kinetic energy or internal kinetic energy equals 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Now, again, we're going to substitute the given to the formula. We would have 1/2 times 0.50 kilogram, our mass 1, 2 meter per second, our velocity 1 squared, plus 1/2 0.500 kilogram, our mass 2, times negative 0.500, our velocity 2, and then squared. After calculating that, we would get 0.763 joule. Now, we have calculated the before. We will calculate the after collision. So, the formula would be internal kinetic energy prime equals 1/2 m1 v prime 1 squared plus 1/2 m2 v prime 2 squared. Again, substituting, we have 1/2 0.50 kilogram times negative 4 meter per second squared plus 1/2 0.500 kilogram 3 times 3.70 meter per second squared. Calculating that, we would get 6.22 joule. Now, we are asked to find the change in internal kinetic energy. So, we again subtract the final to the initial, so that would give us 6.22 joule, our internal kinetic energy prime, minus 0.763 joule, which is our initial internal kinetic energy. So we would get 5.46 joule. So the final velocity of car 2 is large and positive, meaning that it is moving to the right after the collision. So the internal kinetic energy in this collision increases by 5.46 joule. That energy was released by the spring. So it made a significant impact. The spring made a significant impact on the internal kinetic energy, which happens in that inelastic collision. Okay, as a sort of a recap and a summary of my topic, we are going to compare elastic collision to inelastic collision. So, elastic collision conserves momentum and internal kinetic energy, while inelastic collision conserves momentum but changes in internal kinetic energy. So, elastic collision, conservation of kinetic energy, and momentum together allow the final velocities to be calculated in terms of initial velocities and masses in one-dimensional two-body collisions. In inelastic collision, a collision in which the objects stick together, called perfectly inelastic because it reduces internal kinetic energy more than does any other type of inelastic collision. So I highlighted the conservation of internal kinetic energy equation. 1 half m1 v1 squared equals 1 half m1 v prime 1 squared plus 1 half m2 v prime 2 squared, because in elastic collision, the kinetic energy is what we usually used in finding that final velocities and all. So in elastic collision, I highlighted the conservation of momentum equation P1 plus P2 equals P prime 1 plus P prime 2, and momentum, if expanded, it would be M1 V1 plus M2 V2 V2 equals M1 V prime 1 plus M2 V prime 2. Since in elastic collision, momentum is usually used in calculations, so that's what we need to remember in order to calculate and solve for problems. So I hope you have learned and understand elastic collision and inelastic collision in one dimension. Thank you.